Welcome space enthusiasts near and far as we celebrate the successful landing of the Perseverance rover on the surface of Mars. I'm John Serrao, the Deputy Director for Science, Technology, and Engineering at Los Alamos National Laboratory, and I'm thrilled to be able to witness the incredible feat of science and engineering that this landing is, as I'm sure all of you are. We in the Los Alamos community are especially excited because the laboratory once again is playing a major role in one of NASA's Mars missions. Not only is the rover powered by a plutonium heat source developed at Los Alamos, but we also helped develop two of the scientific instruments aboard the rover that will study this Martian surface and tell us whether life ever existed there. Now I'll turn it over to the scientists and engineers who did the work that's very exciting. I hope you take away from tonight's event not only a better understanding of Mars and the science we're currently doing, but perhaps more importantly, have an even broader curiosity for what's out there in space and the discoveries yet to be made.
Thank you, John, and good evening, ladies and gentlemen, boys and girls. Today is February 18th, 2021. It is a hair after 6 p.m. Mountain Standard Time, and just over 4 hours ago, the Perseverance rover landed safely on Mars. To celebrate, Los Alamos National Laboratory brings you this live broadcast from our WebEx studio at the Bradbury Science Museum in downtown Los Alamos. My name is Jeff Favorite. I'm a nuclear engineer here at Los Alamos National Laboratory, and I am your host. Folks, it's a party. So I want you all to get out your Mardi Gras beads from earlier this week and celebrate with us. Los Alamos plays a big role in this mission, and tonight we're going to hear from many of the laboratory employees who have worked on it. You'll be hearing about SuperCam and SHERLOC, two of the 7 scientific instruments that are now on Mars, on board Perseverance, and also about the nuclear power source that will enable the rover to do its work on Mars. First, some notes about WebEx. First of all, you are not alone. It looks like you're partying by yourself. That's to sort of save on bandwidth here at the Bradbury, but there are about 300 people partying with you. Also, for best results, get yourself in full screen mode. Look for an icon possibly on the upper right of your screen with the different view options. And sometimes you'll find that there's a Q&A box that sometimes distorts things, and you can make that go away or appear with the 3 little dots. After our prepared presentations and videos, you'll have a chance to ask your questions. So you can go ahead and type them in the Q&A box whenever they occur to you. All right. So first we'll kick things off with the video from Roger Wiens, who leads the SuperCam team here at Los Alamos.
Welcome to this special 1-hour event commemorating the very significant Los Alamos involvement in NASA's newest and biggest rover mission to our sister planet, Mars. We hope you enjoy every bit of this event as we introduce you to different team members and different aspects of our exploration work. Los Alamos has 3 big parts to the Perseverance rover mission. We led the development and now the exploration with the SuperCam instrument. Like its predecessor ChemCam on the Curiosity rover, SuperCam sits on the top of the mast of the rover, and it looks through a telescope to focus a powerful laser on rocks and soils up to 25 feet away to study their chemical composition. And it takes the highest resolution remote images through that telescope. But SuperCam does much more. NASA called it a Swiss Army knife of instruments because it does so many things. We added 2 techniques to study the mineralogy and the molecular composition of these same spots. And it has a microphone so that for the very first time, we can study the world of acoustics and sounds on Mars. The second role we play in this mission is with the SHERLOC instrument. SHERLOC sits on the end of the rover's arm, and from there it uses a tiny laser, an ultraviolet laser, to interrogate micron-sized spots to make up a map about 1 inch in size of the organic and mineral makeup of that little spot. SHERLOC is a partnership between Los Alamos and JPL, with our lab assembling the detector and the control electronics and programming this instrument. The third role that we play with this mission is to supply the fuel that runs the Perseverance rover. For over 50 years, Los Alamos has powered the NASA spacecraft reaching to the edge of our solar system with Voyager, and to Saturn and Jupiter with Cassini and Galileo, and roving Mars with Curiosity and now with Perseverance. NASA's best and most exciting missions could never be done without the power supplies that only we can provide. And as you have already seen today, Perseverance is the biggest and most capable rover ever to land on the red planet. We will be exploring a fascinating river delta in Jezero Crater and studying carbonate minerals never before encountered in this alien world, and helping to pick samples to be collected for eventual return to Earth. And the world is going to be watching us to see what we pick and how this goes for this historic first part of a round trip to the red planet and eventually back to Earth again. I hope you enjoy this hour as different team members tell how we develop the instruments here at Los Alamos, how we use laboratory instruments to complement the instruments that are on Mars to fulfill our scientific investigations, and how a team of engineers and scientists command the SuperCam and SHERLOC instruments and study their results to reveal to people on Earth the exciting story of the next and greatest mission to Mars. So let's hear from our team members here at Los Alamos on how we're making the Perseverance rover mission a success.
All right, and you will hear from Roger again before this evening is over. Next, we'll hear from the team that helped develop the SuperCam instrument, Steve Storms, the lead mechanical engineer, Benino Sandoval, the lead production engineer, and Anne Olila, a planetary scientist. And after that presentation, you'll have a chance to test your knowledge with our first trivia question of the night. Take it away, Steve.
Well, this has been an incredible day. We're now going to tell you the story of how the SuperCam body unit came to be. Next slide. Hi, I'm Steve.
And I'm Benino.
Hi, I'm Ann.
Next slide. It all began when the science team came up with an exciting new idea. We take something we did before, which was ChemCam on Curiosity, add advanced new capabilities, team up with the French again for the mast unit with the lasers, telescope, and cameras, and have the Spanish provide a calibration target. We put it all on a rover and send it to Mars. We then drive around shooting rocks with lasers. We gather spectra and learn what the rocks are made of. From this, we can learn about the evolution of Mars and look for signs of past life. Next slide. When the engineers heard the idea, we worried about how to make the delicate and precisely aligned optics survive the vibration and shock environments of launch, as well as entry, descent, and landing, plus the thermal extremes the instruments must function in, all of which are conspiring to break the instrument. We have to meet all of the optical, electrical, and mechanical requirements and more, figure out how to pack all the old and new features into a smaller package, and keep it all low mass as possible. All this has to be done on a tight schedule and a fixed launch date. No pressure. Next slide. Once the initial shock wore off, the design process began. We started with what we did before. We added the new capabilities, new electronics, and a lot of other bells and whistles. We then merged them all into a conceptual design. From this, we built an engineering model to verify the concept functioned optically and electrically as expected. We then refined the design from what we learned and added more detail. Once the design was mature, we created detailed mathematical models to verify the design was structurally and thermally robust. Fabrication drawings and procedures were then created to communicate how to build the instrument. We ended with a near final design for fabrication. The design continued to evolve a bit more as we learned more through assembly and testing. All this simplified path were hundreds of iterations within and between steps, and sometimes we had to jump back multiple steps. The overall process took about 5 years from the proposal to the final design. Next slide. Some of the particularly challenging aspects of the design were the addition of the transmission spectrometer, which was new technology requiring the packaging of a lot of delicate optics and developing a new miniature high voltage power supply. Next was switching from beryllium housings and ChemCam to safer but heavier titanium while still keeping the overall mass the same. Then came adding an integrated detector cooling system to keep the detectors at their preferred cold operating temperatures using thermoelectric coolers, heat pipes, and thermal straps. Finally was the need to include decontamination heaters to protect the instrument from fumes inside the rover from coating the optics on its long trip to Mars. Next slide. And here's the final design showing the major subassemblies. It is now ready to move on to fabrication, assembly, and testing. Benino and Ann will take over now and walk you through the challenges of building and testing the SuperCam body unit. On to you, Benino.
Thanks, Steve. Next slide, please. While Steve was in charge of all the detailed engineering design to make SuperCam survive and work properly, my role was more of making sure SuperCam actually existed and getting it to the rover safely. So how do we do that? 6 easy steps is all it takes. Next slide, please. To start out, we get all dressed up, fancy white jumpsuit style. We get all the tiny pieces and put them together. Then we turn on the instrument and make sure it works. Test that it lives through all the crazy environments that Steve mentioned. Take it to NASA for integration and test it with the rover. Next slide, please. But first things first, you got to look like a spaceman to go to Mars. So we suit up and work in a clean room because of something called planetary protection, which means that we want to protect Mars from our biological material. We make sure we aren't breathing out bacteria, shedding hair, or leaving greasy fingerprints all over the rover and its instruments. That way, if we find something organic on Mars, we're sure it was there already, and we don't accidentally start growing aliens on another planet. While all this PPE and cleanroom work makes building the rover more difficult, it's an important part of the process, and it means that we were wearing masks before it was cool. Next slide, please. As an example of how the instrument goes together, you can see all of these lenses and housings which have to get assembled in a very precise and careful way. And that's just one optical subassembly. We have several of these that get built, and they all have to be perfect. Those then get put together to make one of the spectrometers, which in turn gets integrated with the other parts to make the SuperCam body unit. Next slide. In real life, it looks kind of like this. We start out with all the tiny pieces and put them all together with special glues, tiny screws, and even fancy tape, while always wearing our very flattering PPE. And here's Ann to tell you about testing the completed instrument. Next slide.
Thanks, Benino. So yeah, after the engineers get the instrument fully put together, it's my job as one of the scientists on the team to help test it out to make sure everything works just like we want it to. So each of our different techniques need to be tested, and one of our techniques, the laser experiment that blasts rocks, is very sensitive to the atmospheric environment. So we have to bring a little bit of Mars to Earth, and so we built this fancy chamber you see here that can recreate a Martian environment in our lab so that we can test to make sure that the laser is working properly. Next slide. Here's a zoom-in view of that chamber with a dime inside of it that we use to take pictures of with our camera to make sure that that's working properly. We also shot a variety of different rocks and minerals to make sure that the other spectroscopy techniques were working as well. Next slide. And of course, this, like the building of the instrument, took an entire team. So here we have representatives from Los Alamos and France and NASA all working together to test this instrument out. Next slide. Benino?
So, thanks, Ann. For environmental testing and verification, we start in a special lab to test the thermal extremes in vacuum conditions, which means we go hot and cold and cycle between the two temperatures at different pressures. Then we move to a different special lab for shock and vibration, which tests the structural design and integrity of the instrument. Finally, for SuperCam, we even went to an anechoic chamber. There's a special room where we check the electromagnetic emissions of the instrument. Once we're sure it works properly and we can pack it up, we ship it off to NASA's Jet Propulsion Laboratory, the site in charge of building the rover and the Mars 2020 mission. Next slide. All right.
Oop, dang it.
At NASA, the SuperCam shows up in a big wooden box. And inside of that is a plastic box. Well, we'll see if it's working. Jeff, do you mind refreshing that again? Perfect.
It's a slow slide. There we go.
No worries. So you guys see the nice big box, and there's a big plastic box. Inside that is a metal bag and a metal box with stickers plastered all over it. Inside that, we have one last bag and the SuperCam body unit, which we take out and weigh at a very special 4.444 kilograms, which is 4 fours, and exactly the way we designed it. And finally, we take that out, and we get ready to put SuperCam in the rover using a whole team of people and a crane built to move entire spaceships. Back to Anne for more on shooting lasers.
Go to the next slide. Yeah, so as Benito said, once we get to JPL, we shoot the lasers. And so, of course, everybody hits the deck the first time you shoot it just to make sure they don't get zapped. Just kidding. They're just actually setting up an experiment there. Here's an example of the LIDS instrument. That's the chemistry instrument that the laser analyzes the rock with. You can see it firing on this target here. And if we had sound, we could hear it. It would sound like snaps. You can go to the next slide. And we also tested the Raman. This is a molecular spectroscopy technique. So it tells us what minerals are in the rock. And you can see the green laser flashing there. And that mineral that we're shooting is a mineral called calcite. It's one of those carbonate minerals that Roger alluded to in the earlier video that we will be looking for when we get to Jezero Crater. Next slide. And like we had that small chamber to put a Martian atmosphere in for our laser experiment, JPL has a giant Mars chamber that they can change the temperature and the atmospheric pressure and composition, and they put the entire rover into this large chamber. Here you can see it with the mask deployed in the upper left-hand side. Next slide. And here you get a side view in the same room where you can see the wheels and the energy source on the back of the rover there sticking out. And so once the whole instrument or the whole rover is tested and every instrument is tested, then they determine that it's ready to be shipped and everything is good to go. Next slide.
So clearly, developing and deploying a SuperCam is no easy feat. It takes a lot of great people on a bunch of different teams. Next slide, please. To recognize all of those people and their efforts, we make sure everyone gets to sign their work by including these real nameplates on the instruments. Finally, anyone can send their name to Mars through NASA's frequent flyer program, and they'll even send you a boarding pass for the trip. Thanks for joining us, and on to your first trivia question.
Hi, my name is Dawn Vinhouse. I'm a scientist here at Los Alamos National Laboratory. I've been involved in the build and test of SuperCam, and I'll be involved in the operations now that we're on Mars. Our trivia question is, what was the first mission to Mars that included a scientific instrument made at Los Alamos? And the answer? It was the 2001 Mars Odyssey mission, and the instrument was a neutron spectrometer. Los Alamos was initially involved in the Mars Observer mission and provided a neutron and gamma ray spectrometry instrument suite. And that mission was lost en route to Mars in 1993. That involvement led to the Mars Odyssey instrument, which was led by Bill Feldman. The instrument allows us to map the water content, the near-surface water content on Mars, and it showed that there's plentiful water ice in the upper latitudes near the poles. And we also found that there was water-bearing clay minerals scattered across Mars.
Next, we have a video from Jackie Lopez Barlow, who manages the program at the laboratory that provides nuclear power to space missions. She'll tell you about the nuclear battery that powers the Perseverance rover.
An RTG is a radioisotope thermoelectric generator, and what it is it's a battery. We have our heat source in the middle, which contains the plutonium-238 fuel clads in a module form, and then that gets assembled into the full RTG, and it takes the heat that is generated from the plutonium and gets converted into electricity. Plutonium-238 in itself generates thermal energy due to its radioactivity and the decay process. Pu-238 has a long half-life, which is really good. It's about 84 years, so that's what makes it really good to take into environments where you can't have solar or you can't rely on solar, as an example, for long periods of time. Los Alamos' job is to be the production agency for manufacturing the Pu-238 heat sources. These are fuel clads that have the plutonium inside of it that has been put into a pellet form, a ceramic pellet, and stabilized, then gets welded into an iridium clad body, which we get from Oak Ridge National Laboratory, and then we get that and send it over to Idaho National Laboratory, where it'll eventually get assembled into the MMRTG. What is really good about what we've seen in previous New Horizons, Voyager, is we're able to exceed the life of certain missions. Where we're going in those deep space missions, it wouldn't be possible with any other type of heat source. You need to be able to have that continuous power source available to you. You can't do that with solar energy. As an example, Dragonfly is going to be going to Titan, and that wouldn't be possible without having nuclear powered power systems. It's amazing. It's to know that you're a part of this and knowing you were able to provide a vital piece that allows everything to work. It's so exciting. We have an amazing team of people who were able to accomplish all of this. Even historical missions that our team members have been able to support for Cassini, New Horizons, the other Mars rovers. It really puts you in this small group of people who can actually say, I was part of that, and that there's a lot of pride in that.
All right. Now we'll learn about the SuperCam lab, where they zap rocks on Earth here in Los Alamos before they zap rocks on Mars. And here to tell you about that are physicists Adriana Reyes Newell and Ray Newell. And they're not masked and they're not social distancing, everyone. Stop the tape. What's going on?
Same household.
Same household. Explain.
We're about to celebrate 20 years of marriage.
Wow. Another great achievement. Go ahead, you guys.
Thanks very much. It's an honor to be here. Thank you for asking us to come and present a little bit of the work that we've done here for the SuperCam and SHERLOC projects. I'm Ray.
I'm Adriana Reyes Newell.
And we could go to the next slide, please. So here's a photograph taken in one of our laboratories in the hall. As Benino alluded to earlier, it's very important that all of these instruments be kept clean. And in fact, the two units there that you can see behind us are the flight units, but they're inside of a clean room with those clear plexiglass walls that you can see behind us. So you can see those, this was taken just before those are packaged up and shipped off to integration with the rest of the rover body in the boxes that Benino showed earlier. Next slide, please. To give a sense of scale and sort of the work that goes into this, in Benino and Steve's talk earlier, you got to see an exploded diagram, by which I mean all the interior parts of one of the optical instruments on board this onboard SuperCam, which we call the transmission spectrometer.
Which I have to interject and say Ray designed all of the optical paths,
That's
and
true.
that wasn't mentioned.
That's true. I did. Yeah, thanks. That was fun. It was a good project. To be able to make sure that everything stays in focus so that we get the best possible images and the best possible science data return, it's important to align all those optics, right? So all that you saw in that diagram that Benina showed earlier are the adjustment points in the lens barrels, very much like an SLR camera that you might have at home, whereby rotating things around, you can adjust the focus to make everything be just the way that you want it to be, both on Earth and in Mars, which of course is different. It's a thermal environment that's very different. Mars is both hotter and colder, depending on time of day and what else is going on. And Mars has very, very little atmosphere. So the index of refraction of air in the atmosphere there is very different from here. And all these things need to be taken into account when doing the alignment of the optical systems, which is what you see taking place in this picture here. Here I am inside one of the clean rooms with some software that we've written in the back, showing the alignment of the spectrometer to really optimize its performance before shipment. Next slide, please. Once everything was set to integration to the rest of the rover, of course, we also had to make sure that it was working after being installed and connected to all the rest of the rover systems. So this is a fun photograph similar to the ones that Anne showed earlier. In this instance, you can see up on top of that pedestal a very special camera that's used to record an image of the laser beam to make sure that all of the laser beams and all of the cameras on board SuperCam are aligned with one another in the way that they should be and are working appropriately and all working together. Next slide, please. And of course, if you ever have a chance to take a selfie in front of a Mars robot, you should take that opportunity by all means. Here, let's go. So here's a selfie showing the protective gear that we use when doing this work. You can see that I'm wearing laser safety glasses to protect my eyes from that very powerful rover, very powerful laser, excuse me. If it's powerful enough to vaporize a small bit of rocks, it's certainly powerful enough to injure a person. So we wear protective goggles to keep that from happening. And we also wear all these protective gowns, this clean room uniform, this coverall with masks and everything else to protect the rover from us, right? Everything that goes to Mars must be very clean. Next slide, please. It all comes together, and here's the two of us standing on, right in front of it to give a sense of scale of the rover. This thing really is big. It is the size of a full-size SUV, and it's quite tall, and it's really a wonderful instrument. We're very glad and proud to be able to work on it. Next slide, please. In addition to the instrument that has recently just now landed on Mars, there are two Earth-based instruments which are used to gather complementary data, which Adriana will discuss in just a moment. But here's a photograph of one of those Earth-based instruments. One of them is in our laboratory here in Los Alamos, and another is in our colleagues' laboratories in France. And here is a photograph of several of this being unboxed and on display. Next slide, please. I think we have here a brief video to show what this looks like in use and being hooked up. There we go. There's the part of the shipping container coming off to reveal inside this absolutely gorgeous gold-plated set of assemblies. The one that I'm removing the cover from right now is the mast unit. This unit contains the telescope and laser and was produced by our colleagues in France. There you can see the output of that laser and telescope. Go ahead.
And right here, I am integrating the fiber, or removing the fiber from the spectrometer part that gets us the information after the laser fires, and we get a plasma spark. The telescope collects that light and sends it to the spectrometers, where it gets analyzed into the different color components to tell us what the chemical composition of what we're shooting is. Next slide, please. So in addition to SuperCam, I will be, just like I do for ChemCam, currently in the laboratory, they have, the Earth-based model. I will be monitoring and using the Earth-based model for SuperCam to run comparative suites of tests, just like they run the Perseverance or Curiosity rover, each with ChemCam or SuperCam. And I will be doing tests to compare the results and make sure that we can validate the results. Next slide, please. So here, just like Anne was mentioning, I have a Mars chamber that simulates the atmosphere and temperature of Mars, and I put the samples inside, and the samples can be anything from actual rocks to pressed powders that contain specific amounts of a specific chemical that we want to test in a matrix form. Next slide. Here is the actual plasma under Earth conditions, basically not as big as they would be under Mars conditions because the plasma expands, but shooting some rocks, and the different colors show the different compositions of what the material is, what I'm shooting at. Next slide, please. One exciting aspect of this technique that we have is called LIBS, is that we want to try and determine the material composition based on how deep the pits go in different materials. So a material that is soft will have a very deep laser mark, whereas something that is very hard will have a shallower pit. And we want to use that diagnostic to be able to, before knowing what the composition is, know what it's made out of and its hardness. Next slide, please. And I want to mention that these small pits are about 250, 300 microns across. And if you think of a hair as being 100 microns, these are very small pits that can give us a wealth of information and all kinds of parameters about the rocks or materials that we're looking at. For example, here I have a set of pressed samples that I can interrogate with the laser by shooting it and determine what the materials are as a function of a specific chemical. Next slide, please. A fun part of my job is to share all this excitement with students, and for the past few years we've had a summer camp for a physics camp for young women. And we brought them to the laboratory where they get to experience real time. I get to shoot a rock in front of them in the Mars chamber and show them the LIBS spark. Everybody has to wear their special laser goggles, in which we all look so cool. And unfortunately, we haven't been able to do this with COVID, but we did a summer physics camp virtually where they had lasers at home, and they did not spark inducing experiments, but played with optics and learned about everything else that we do in the laboratory. Next slide, and I think that's it.
I think next up we have another trivia question.
Hi, I'm Chip Leggett. I'm a geoscientist working on SuperCam on the Perseverance rover. How many sample tubes is the Perseverance rover carrying to be used to collect samples on the surface of Mars? 38. Perseverance has an important task to collect either solid rock with its drill or loose soil samples. Each tube is about 5.5 inches long and 1/2 inch in diameter. Eventually, Perseverance will leave these tubes on the surface to be collected by a future mission. A major task of SuperCam, SHERLOC, and the other instruments on the rover is to find the best place to collect these samples.
All right, here's the SuperCam. And Perseverance rover, of course, we can't, I'm at the Bradbury Science Museum, so we can't have champagne, but I have coffee here in my champagne glass, so here's to you guys. How do we pick the rocks to zap on Mars? Well, Scott Robinson and Tony Nelson will now tell you. Scott and Tony are, at this moment, busily making sure that the rover is working as it should be, so their presentation was recorded earlier. And afterward, we'll have the last trivia question of the night.
Hello, my name is Tony Nelson.
And I'm Scott Robinson, and today we'll talk to you about doing operations with SuperCam on Mars. So I've been with the laboratory over 30 years. I was the instrument manager while we were building and delivering SuperCam, and now I'll be supporting operations.
And I've been at Los Alamos for over 20 years. I've done a lot of electronics design for our various instrumentation for satellites and rovers and so on. But I'm also helping with instrument operations for SuperCam. And we are just 2 members of a very large team throughout the world, including many of us at LANL.
Tony and I are actually recording this segment because we are doing operations while you're watching this. It's the first shift after the rover has landed on Mars.
We mentioned we have this large international team, including many of us at Los Alamos. This includes both scientists and engineers. And this is a collaborative effort, not only with us here at LANL, but also our partners throughout the world. We essentially work remotely over a WebEx, and you can kind of see how this would work if we were working at LANL at the moment. A shared screen, and we're discussing what the rover should do for a given sol, which is a day on Mars. On the SuperCam team, our job is to essentially send commands to SuperCam and then check the return data of the science that the instrument returns.
Doing operations with SuperCam is a complicated sequence of steps that starts with data from the rover being relayed through orbiters around Mars to Earth. We then look at that data and pull out state of health information and science information for immediate analysis. From that, we look at potential targets around the rover using the long-term science plan and goals, along with targets of opportunity that are around the rover. From that, we prepare a sequence of science observations and put that together with the other activities that the rover is planning, the other instruments on the rover, the other operations the rover needs to do, such as driving and maintaining communications. That's all put together, and from that, commands are created. Sequences are put together that direct the instrument on how to point and collect the science data that's of interest. That's put together with everything else the rover needs to do, uplinked again through orbiters around Mars, and eventually down to the rover.
Scott mentioned the targets on which we're collecting this SuperCam data. You can see here an image of one of that's collected around the rover after it gets to a new position following a drive. These red dots represent a couple of targets that the science team might be interested in. SuperCam can collect data from these targets in what are called rasters. And these are just micro targets on the surface of this, in this example, rock, and at a very fine scale, at millimeter scale. This allows us to interrogate the rock for very fine details. For example, if we had shot a little higher, we might have hit this vein in this rock.
Some of the data we receive from SuperCam is state of health information. It'll tell us temperatures and voltages of the different parts of the instrument that we look at. The chart here is an example of temperatures during a collection operation and how it varies over time. From this, we can assess instrument performance and its health.
SuperCam has a number of observation modes that yield different types of spectra in its science return. Lib spectra is a high-powered laser that fires on the surface of Mars that will yield the elemental composition of the rock or soil that it was targeted. in a number of different spectrometers that you see here. These represent different wavelengths of light, essentially. Raman spectra is another observation mode that SuperCam has, and this gives us the mineralogy of the rocks or soils we're targeting. There's an infrared spectrometer that is essentially a passive mode that does not use a laser, that based on the light that's reflected off the surface of Mars or in the atmosphere, we can determine the types of minerals we're looking at. There's also a microphone on SuperCam, which can be used to record such things such as the wind on Mars, the rover doing different types of observations, such as moving the arm, so we'll hear the mechanisms moving. Or it could be used while shooting our laser, our LIBS laser, which makes a very characteristic sparking sound. So in this example, you can see a couple of different peaks representing those sparks. Lastly, we have a context image, which shows us the area on Mars where we targeted. This is a very zoomed in view that gives us detail of what we might have hit on the surface of Mars. All of this data is processed and then compiled, and then over time it will be analyzed further and then make its way into publications. Once again, I'm Tony Nelson.
And I'm Scott Robinson.
And thanks for listening. Go SuperCam, go Perseverance.
Hello, my name is Dot DeLapp. I am a computer scientist at Los Alamos National Laboratory. I work on processing data from ChemCam, which is an instrument that's on Curiosity. I also process the data for calibrating SuperCam, which is an instrument on Perseverance. Mars is a dusty place. To analyze the rock samples, the rover's instruments need to first clean off the dust. SuperCam blasts the dust away with its laser. Perseverance has one other way to get dust off the rocks it analyzes. What is it? A small blast of compressed air. The rover's arm contains a reservoir of compressed air as part of a gas dust removal tool, GDRT, GDRT. Previous rovers used brushes, but they were not as effective as the compressed air. The SHERLOC instrument will use GDRT to remove the dust for its analysis.
It is a party here at the Bradbury Science Museum. We got a marching band playing back there. We've got balloon animals. So sorry that actually I'm in front of a green screen, so we lost a little bit of Marvin, but phew, it's a party. We've been talking about SuperCam tonight because SuperCam just arrived at Mars, but before there was SuperCam, there was ChemCam. ChemCam landed on Mars almost a decade ago on the Curiosity rover, and it's been providing us with scientific data ever since then. Now here's another video of Roger Wiens to tell us a little bit more about ChemCam and about how SuperCam wouldn't be possible without it.
ChemCam is the precursor to SuperCam. It uses a laser beam to target rocks and soils up to 25 feet away to study their chemical composition. We started working on ChemCam way back in 2005, and it's been on Mars since 2012 with the Curiosity rover. It is highly innovative. We were inventing this new technique as we went along building it. Among its discoveries, it contributed to our understanding of the large lake that lasted for a long time in Gale Crater, which is its exploration site. It showed for the first time that soil carries about as much water on Mars as in southern New Mexico on a summer day. That is amazing for a planet that we thought was so dry. It contributed to our understanding of Mars as an igneous planet that does not have plate tectonics. It discovered manganese deposited in very oxidized groundwater. That shows that Mars possesses the oxidation potential needed for life. Beyond that, ChemCam discovered boron, left over from groundwater flowing long ago through cracks in the rocks. Boron is an essential ingredient for RNA to survive in solution. It identified copper and zinc deposits that are somewhere upstream of Gale Crater. And now it's telling the story of how Mars started to dry out after this wet epoch. Overall, ChemCam, which is operated from Los Alamos, has returned over 1 million spectra from the red planet, and we've published 102 scientific papers highlighting ChemCam and its discoveries, a wealth of information. So it's no wonder that NASA has picked SuperCam to be its successor.
Woo! Oop, dud. All right, now we will hear live from Roger Wiens, from Sam Clegg, and from Nina Lanza to tell us more about what we hope to learn from both SuperCam and SHERLOC as Perseverance begins roaming the Martian surface.
Okay, voice check.
We hear you. Go, Roger. Thank you.
All right, let's go.
Hey,
to
you
the
look
first
good, and
slide.
that's a great tie, too.
You know, I have to tell you, since you mentioned it, this tie showed up in a FedEx package on my doorstep an hour before this party, and it's all about Perseverance, and the helicopter is right near the neck part of it.
Excellent.
And so I had to wear this. I think somebody in the audience sent it. So anyway, let's go. Next slide.
Yes, I recognize that.
Perseverance is on the ground, and if you didn't see it before, this is the first picture, just a sweet picture. It was so fun to watch this landing, and this was the first landing that I actually got to watch with my family. So thanks to COVID, but I'm happiest of all the landings. So let's go on. The question is, next slide, what are we going to do now? We're on the ground. Well, it turns out Percy's not really quite ready to rock and roll. First of all, the mast is still stowed on the deck of the rover, and SuperCam's on that mast, so if we were to shoot the laser now, it'd be shooting the rover. Then the other thing is that the rover still has software that is set to help it to fly to Mars. And so it has to do a complete change of software to be ready to roll on the Martian planet. And then, as you can see, the arm is stowed, and so to get to SHERLOC, we've got to start getting that arm out and deploying it. So all of these things are going to be happening sort of day by day. We do hope to make a early check of SuperCam's health the next day, sending up those commands hopefully tonight. And then the mast will get deployed. There is actually an explosive that cuts a cable right next to SuperCam, and so there's a little bit of risk left yet, but we hope that all goes well over the next several days. That software is supposed to get loaded kind of mid next week, and SuperCam is getting a new software load as well. And so it's going to take a little while to unpack all of this. It's almost like moving to a new house. You don't just get going right away. There's a whole lot of things that you got to unpack, and that's very true of this rover. It's going to be sometime, probably a little over a month from now, actually, when the helicopter gets to fly. And so then after those flights, then we're really going to start getting down to the science that we're going to do. But, there's things that we'll be interspersing during this time. We hope to be starting to use SuperCam within a few days, little bits and pieces, probably starting with a microphone. And in fact, I think next slide. I think Nina is going to tell us something about this microphone a little more than we've heard already.
Yes, thank you, Roger. Yeah, so we've heard a lot about the instruments that make up SuperCam. We've got lasers that vaporize rocks. We've got spectrometers. We've got a camera. But what's up with this microphone, right? What are we doing? You can see here in this red circle, that's where it is. So the microphone is on the mast unit, right on the head of the rover. So it's like it has one ear and one eye. And so the reason that we're going to have this microphone is actually, it's going to be the first time we're going to hear the sounds of Mars. And it's not just to hear the Martians and what they have to say to us, right? We're actually going to hear the ambient sounds that Mars makes, the wind, the dust devils. This is going to be the very first time we've done this. But the main reason we actually put this on there is to hear the sound of our laser as it zaps rocks, because it turns out that when we hear that sound, it will tell us something about the material that we're zapping. So how hard it is, how deep we're drilling into it. And I'm very excited to see if there might be some thin layers like rock coatings on the surface of some rocks, because this is a great place in which to look for habitable environments. So places where life might exist, life like microbes. So this is a really exciting new capability. And so I can't wait till we turn it on. It's really soon. If you can't wait and you want to hear what it might sound like on Mars, there's a great website you can go to where you can hear a simulation of what sounds sound like on Mars and compare those to Earth. And so this is a long website here, but if you just Google sounds of Mars, you can get there. So you can wait for a few Martian days before you can actually hear the actual sounds from Mars. So stay tuned. Next slide. So we landed in a place called Jezero Crater. So this is not a photograph. This is a computer-generated image of what Jezero might have looked like 3.5 billion years ago. Just from orbital data, it looks like this was once a lake, a long-lasting lake. And this is coming from mineralogical and morphological shapes, features that we've seen from orbit. You can see this is a really big lake. So you can see here, Jezero is about 28 miles in diameter, and that's pretty comparable to Lake Tahoe, a terrestrial lake you might be familiar with. This is a really big lake, and Lake Tahoe is very habitable. It's a place where life certainly can exist. So we think that Jezero was a place that Martian life, if it existed, could have been there. Now, we don't know if Jezero Lake was inhabited, but we're going there to find out. And so if we go to the next slide, I think Roger will tell you a little bit more about this landing site.
Yeah, so here we are, and you can see some really interesting things right here. There is, you can see the ellipse where the rover was targeted to land, and it's really near this inlet channel and this delta formation. So as the river was flowing, it was bringing sediments down, and just like the Mississippi River or some other large river, it deposited material as it flowed into the body of water. Now, if we take the next time step on this slide, you'll start to see a zoom-in area of this. And by the way, the rover landed sort of in the lower right-hand part of that zoomed-in image. So we've got just a few kilometers, a couple of miles to go to get to the delta. But we have never landed anywhere near or explored a river delta on another planet. And so that's why this is such an exciting place to go. Now we know that there's some interesting chemistry and mineralogy in and around this delta and around the edge of this former lake. And so, Sam Clegg, I think you're going to tell us a little bit about the chemistry and mineralogy we're going to be looking for.
Thanks, Roger. We can go to the next step in the slide. Great. Yeah, so there's some instruments that are in orbit around Mars that allow us to get some sense of the mineralogy that's in and around the landing site, including highlighted in red would be olivine, which is a silicate. In green or yellow, that's a magnesium carbonate mineral. And that's really going to be exciting to investigate because it's really quite rare. In fact, remarkably rare to be able to find carbonates on the surface of Mars, despite the fact that the atmosphere is made up primarily of carbon dioxide. In addition, the blue highlighted regions are dominated by things like iron and magnesium smectite, which is a clay material. And so it's expected that water from this area would have deposited these structures, these minerals, into what was a lake at Jezero, and that it's conceivable that these minerals would have supported early microbial life in Jezero. Next slide, please. So this is how we actually will use SuperCam. These are actually images from ChemCam, and a couple of things to point out here. One is, as you heard about earlier, about dust. When we focus our laser down to spot sizes that are less than 1 millimeter in diameter, usually about 0.2 to 0.3, 0.4 millimeters in diameter, that shock wave that's produced does a really good job of removing the dust. So you can see that in the top image, where you see dust everywhere except where those laser spots are indicated. And we usually will do rasters, like you heard earlier, so we get a pretty good idea of what the rock or the soil looks like by looking at a number of spots in the same area. The small spot size that that SuperCam uses also allows us to look at really fine-grained materials, like the crystal-like structures you see in the bottom left image. And just like Curiosity, the Perseverance rover includes a drill, and the ChemCam and SuperCam instruments are the only instruments that actually can probe the wall that's left after the drill finishes its job. And so you can see in the bottom right corner a number of what are laser spots. And it gives us a really good indication of what that material was that we just drilled out, or in the case of Perseverance, that we just collected. Next slide. And then we're also very excited to be part of the SHERLOC team. SHERLOC is a Raman and luminescence instrument that's designed it sits on the end of the arm, and it's designed to look for organics and chemical analysis. And so the rock, or the picture you see at the top of this, is a stromatolite, which is a layered rock material. And this is the earliest fossil evidence that life was of life on Earth. The bottom left image is a grayscale image of a part of the stromatolite, and in various spots on this image, a Raman and fluorescence spectrum would be collected that tells us what that rock is made of, including things like, in this case, organics, a dolomite, or a chert. And then on the right-hand side, that information is converted into a map that shows the relative abundance of these minerals, including the organics in green, a dolomite in red, and a chert, which is a silicate, in red. So it produces a nice map of the minerals that are present in the samples that we'll analyze with SHERLOC. And with that, I'll hand it back to Roger.
Thank you, Sam and Nina. Next slide, please. So not only is Perseverance interested in studying these chemistries and mineralogies and textures to understand the ancient Jezero Lake, not only to do some new technologies as well, but Perseverance is the first part of what we believe will be a three mission set to bring samples back to Earth. Whenever we send a rover to Mars so far, that rover just stays there forever. There's no rocket. Nobody's building rockets on Mars to send it back. But we're planning to change that, because if we're going to send astronauts to Mars someday, we got to prove that we can get them back. And so Perseverance is designed to be the first leg of this set of 3 missions. So Perseverance will be collecting these samples with a drill. I'll show you in just a second. And then those samples get loaded into the nose of a rocket that is supposed to come on a following mission, and launched into low orbit around Mars, where it rendezvous with yet another spacecraft, which will then ferry it back to Earth and re-enter it into Earth's atmosphere. And so we are starting this historic first round trip to Mars and back. Next slide. So to do that, there's a little video here that shows how the drill collects samples. So the drill is hollow, and it has a rock sample inside it after it's drilled. And here is bringing that core into the rover, and it in a metal tube goes into this turret that brings it into a vertical position where another arm comes and takes it. That arm puts it into a place where they get a picture of what's down the tube. And then there's a capping station. They're not shown here in this video. And then it goes into a storage space on the left. And that storage space has enough space for all 38 empty tubes right now, and that is where it will stay while the rover does a number of sample collections. Once there are a number of samples collected and the whole science community decides, yes, it's time to put these samples down, there will be a place called a sample depot. Next slide. And so somewhere on the surface of Mars where this rover drives, we're going to designate as the drop-off place. And so you see one of these sample depots here. I hope actually the sample depot looks a little more organized than it does here where the tubes are quite scattered. But you can see the rover is photographing the exact spot. It's probably also getting the coordinates of exactly where this is so that we will have no question that we'll be able to find this place in the future again. And there may be a couple sample depots, maybe even more than that, with groups of samples that will be laid on the ground for the future return mission. And so that is how this mission is leading into what we think will be following missions to eventually get us samples on Earth, where we have even more complicated and accurate instruments that will be able to study more about organics or other aspects of the samples that we will get back from Mars. And so next slide, we'll just leave you with this picture of the two instruments, SuperCam and SHERLOC, that we've contributed to and are leading, and just really looking forward to using these instruments. Also, thanks a huge amount to everyone that was involved in the power supply that is powering this rover every day, day in and day out. And we'll leave that there. I'll leave it there and give it back to you, the microphone back to you, Jeff. Thanks so much.
All right. Well, folks, that concludes our somewhat organized presentations. And now the super fun part is we get to answer your questions, many of which have already rolled in. So one of the things that has rolled in already is, why are the samples left on the surface when they've been stored in the body? Why are they ejected from the body and tossed on the surface?
Nina, you want to take that one, or shall I? Why don't you take it, Nina?
Sure, yeah. You know, it seems a little counterintuitive, right? You'd want to keep all your samples organized in that rover, but the trouble is, what if the rover gets stuck somewhere and the spacecraft that comes to get those samples can't access it? Well, now all of your samples are stuck in that rover and they won't come back to Earth. And so it's actually much easier for a spacecraft to come get those samples if they are lying on the ground somewhere. And we actually don't necessarily want to put them all in one pile, right? Because we don't know, what will happen over time, and if they get maybe a little bit buried, or if it's a harder landing spot than we thought it was going to be. So what we're going to do is we're going to spread out our samples on the surface so that we can actually get at least some of them, if we can't get all of them. We want all of them, but if we can only get, say, one of them back, that's still better than none of them. So that's why we're doing that.
All right, thanks, Nina. Richard Whitmore and I are both wondering, Roger, you said that one of the first things to do is download the software. Why wasn't the software on board when it left?
Oh, Jeff, I suppose that's a good question, and maybe I don't know the exact answer, but I can tell you a few details about that. So Perseverance was made to be a fair amount like Curiosity, in part to be less costly for the American taxpayer. And so a lot of things were used over that were used on Curiosity. One of the things was the onboard computer. And if you think about it, computers have advanced just a little bit in the last 10 years. But they actually did add one additional processor, so they have 3 processors instead of 2. But there's a limited amount of memory. And there's a lot of software that we load this rover with. It's going to figure out exactly where to shoot SuperCam on its own eventually, things like that. And so we need that software memory, and the cruise phase of this mission needed that software memory too. And so the best way to do it is to get it on the ground and have a new software upload and a day or two of testing that, and then off we go. And that's not a problem. We can do that in the next few days.
All right. Thank you. Another question that came in is these lenses. We know how dusty Mars is. How do you keep the lenses free of dust?
Sam, you want to answer that one?
Or Ray?
Or Ray.
Or Ray?
Go ahead, Ray.
All right.
Yeah,
Okay.
go for it. Ray.
Thanks. We can both chime in. Plenty of time. So the question was about how do we clear dust from the lenses? Short answer is we don't. Dust gradually does accumulate over the course of the rover's lifetime, over the course of the mission. And quite a bit of work was done primarily by our colleagues in France to make sure that when that very high power laser, when all that light comes out the window, comes out that last optic, the one that will get some dust on it, of course, some of that light is going to hit the dust. That dust is going to get very hot as a result, and we need to make sure that heating, that thermal damage from the light hitting the dust doesn't degrade or impact or otherwise damage the optical coatings that are on the surface of that window. So our colleagues in France put actually quite a bit of effort into this, making sure that that beam was spread out enough, that it's not so intense that dust particles are going to absorb too much light, just from an intensity of the light issue. But yes, and then of course we're always grateful when a dust devil or some little windstorm comes along and sweeps things off for us. That's very difficult to coordinate and not something we can plan. But when it happens, that's good. But yeah, overall, we generally treat dust as a gradual degradation of performance over the lifetime of the instrument, rather than something that we actively manage. It's a great question.
Good, thank you. A lot of people out there are really curious about the gold that we just sent to Mars and probably will never get back. I'm going to use MC prerogative here and call out Benino, who answered this question in the chat. But Benino, can you put that in English for everyone? You're muted.
I got it. Double mute. Got me every time. So first off, to address all the gold that we're sending that we're not getting back, it's actually a very, very thin layer of gold. Significantly smaller than a single millimeter.
Okay.
Just for everyone who's out there, these aren't gold solid, they're gold plated. And so the idea behind the gold, there are many reasons that we use various coatings for instruments and for spacecraft. But one of the main reasons that we use gold is that it has a very, very low thermal radiative emissivity. And what that means
That's
is
what I was hoping to avoid. Okay.
Heat, yeah. So just like all of us, if you think of infrared, like night vision goggles that look at things, they're looking at your heat signature. And so this is commonly used in pop culture where they're, trying to find the bad guy and they can zoom in on, oh, there's his body because he's radiating heat. And so that's a real phenomenon. And one way that you change the amount of heat that a surface is giving off is by changing the surface coating. We call it the surface emissivity. And so gold lets off very little heat, and so that's why we use it.
Great, thank you. Nina Lanza, I don't know if we mentioned, there looked like there were two microphones, and people were wondering about that. Why are there two? Are there really two, or did we just missee that, or why are there two?
There are two. That's a really good question. So, of course, more microphones, more better, right? Of course, we want more. But one of those microphones is on SuperCam, and we're doing science with it. And the other is the entry, descent, and landing microphone, or EDL microphone. That microphone is something that JPL put on the rover to actually get the sounds of the landing as it happens. So I'm super excited to hear what that sounds like screaming through the Martian atmosphere. That's going to be really great to go with our video of landing. And so that EDL microphone, it's only supposed to last for entry, descent, and landing, but we're hoping that it will continue to last so that we can actually coordinate with that microphone to do experiments, because we can learn a lot about sound by putting two different microphones at two different places. So we can actually record the same thing and learn more about the nature of the sound and also the nature of the Martian atmosphere. So good eye, yes, we do have two microphones.
Good, it was not my eye. So how long? It will be 2 months before we get to start collecting data. And then Roger said that we have a couple of miles to go before we get to where we really want to be in the Delta. Can you explain that again? What's our first move after we get unpacked?
Oh, yeah. So we're not waiting that long to take data. We'll be starting to take data right away, but it's a little slow at first, and then we get better at it, or smoother as it goes. But we got to spend a little time at the beginning checking things out. But really, yeah, we're hoping to get a health check from our instrument. Then the mast is supposed to be deployed. Get data from that by Sunday of this coming week. And once the mast is deployed, then we can start getting those pictures looking all around the rover, and so then we'll start to really see the surroundings really well. And then we'll just little by little start adding different features of SuperCam, of the other instruments, and so on. There's also a lot of interest in the area where we're at now. We want to get a sample of what might be a volcanic rock. And so that's below the delta, and then there's other features we want to study as well before we get there. So lots to do already at the beginning, but the data is going to start coming slowly at first. You just have to be a little patient with us.
I think we can do that. So one final question is, once we do get rolling, and okay, first of all, I told a bunch of kids today that you guys call Perseverance Percy, and so far nobody has done that. Please tell the children that you do call Perseverance Percy.
Yes, we do, absolutely.
Can you at least say it? Say Percy.
We refer to the rover as Percy.
Okay, thank you, Ray.
This afternoon.
Kids think Mr. Favorite is a big liar, but
we were all watching that video. We're like, come on, Percy, come on, Percy, you can do it, come on.
That's great. So, okay, and here's a model. That's good, Adriana. So my last question, which a couple of people have written in, once we do start moving, how far will Percy roll in a day, and sort of how does that compare with how far Curiosity is going?
Let's see, Sam, we haven't heard an answer from you. Would you be willing to take this one?
I can try. I heard this morning in one of the briefings that it's got cameras and software on it that allow it to move much farther and probably a lot faster than Curiosity did. I thought I heard 200 meters. But please correct me if I'm wrong, Roger.
That's right, I believe. Yeah.
So it is more. It can drive faster, a little faster and a little farther than what we can do with Curiosity on a given fall.
Okay. Well, thank you all to the Los Alamos scientists for being here tonight. And thank you all out there in WebEx land. Thank you for joining us tonight, February 18th, 2021. Congratulations. And as Roger said, a big, big thank you to the huge team of scientists and engineers who landed Perseverance safely on Mars this afternoon. And good luck and break a leg, Roger, you and your team here at Los Alamos, and to the hundreds of people around the world who will be deploying instruments and doing checkouts as Percy gets ready to start roving. We can't wait to see what Percy will find. Thanks to Mel Strong here in the WebEx studio, and thanks to Laura Mullane for organizing this event. Thanks a lot to my friend Robert Lopez for making Marvin the Martian for us. I'm Jeff Favorite. Thanks for joining us. Good night, everybody.